Well, hi everybody. I figured I'd just make a little video to try to walk through some of my solutions here to missions 6, 7, and 8, I guess. And I'll just say at the start of this that I've tried not to let perfect be the enemy of good, so not all of these solutions are what I would say complete. But anyway, let's get into it. So here's the formal statement of the problems. Of course, I've got this linked on the website, so you can look at it there as well. Anyway, let's get into it. So, excuse me. All right. So, to start with, you're given this smooth tensor field, and so at a point, it maps pairs of tangent vectors and a covector to the real numbers, right? So if I want to understand the coordinate change properties of such a thing, what I want to do, right, and let me go ahead and change this up a bit here. So what I want to do then is I first understand how does a tensor work in terms of how it acts on the basis, right? So basically, you know, if you feed it a vector VW and a covector alpha, those expand into the, what am I doing here? It's the right job for the tool for the job. So you gotta have here. There we go. Anyway, so this is partial x and partial xj and dxk apparently, and by linearity I can pull the sums and the constants out at the point, or if you're thinking about not having a point but letting these be vector fields and differential form fields, you can pull out smooth functions in that sense. And what you're left with here is this, you know, the components of the inputs against this thing, which is characteristic of S, which we call the components of S. These are the components of S with respect to the x-coordinate chart. Now, if I did the same song and dance for the y-coordinate chart, I decided to switch my y to an x bar just for the sake of the bar coordinate scheme here. Then I'd get this formula in the same way. And that would define the S bar ijk components, right? And then to relate these two components, it all basically boils back down to the chain rule. The chain rule tells us how to relate, you know, partial derivatives with respect to one coordinate system and differentials with respect to one coordinate system and another. They transform inversely, actually. These are inverse matrices, truth be told. And so if you put that all together and you just basically plug this formula and this formula up into here, then you can derive the coordinate change rule down here like so. And that's how it goes. We get, you know, for each lower index, we get one of these guys, and for each upper index, we get one of those guys. And if you had more indices, the song would remain the same, so to speak, you know. So there's that one. Now, next one here, let's see here, problem 58, I believe it was. You got this here. See, I should have kept my problem sheet out to do that. So problem 58, you got this. You give a tensor and a map, and I'm supposed to calculate the pullback of the tensor under the map. So what that amounts to doing is just substitution of the formulas for the map into the tensor. Like once we got through the formalism, what the pullback meant, what it calculationally amounts to is a substitution. So I did that. I have x is u plus v, y is v plus w, and so I set that equal to that, and my apologies for this problem, because, yeah. So, I'm sorry. I mean, I don't think we get a lot of insight from this problem. You know, you win some, you lose some. Anyway, it's a problem. We did it. Now we're done with it. Let's see here. Next one, maybe it's more interesting. I don't know. Maybe. Is you got this set of rank 2 covariant tensors. So question A asks you to decompose that rank 2 tensor into a sum of a symmetric and an anti-symmetric tensor. And so this is the standard trick. You can write that plus that, and of course you just added 0, and this is symmetric, and that's anti-symmetric. So in my notation for the problem, TS is an element of BS, and TA is an element of a BA, and I'll let you guys check the bilinearity. Now, I thought I had some kind of smart calculation here, and then I was like, wait a minute, what am I doing? I should go back to my standard calculation, which I give here. So to show that the that an antisymmetric tensor can be written in terms of the wedge product of the differentials, what I do is I break the sum into a sum over I less than j and I greater than j. I equals to j is nothing because TII is equal to 0 by the antisymmetry. And so I do that, then I relabel the sum with k and l, but I do it differently. I set I equal to k and j equals to l on this one, but over here I set I equals to k and j equals to whatever, the opposite of what I just said. As you can see, the pattern's different. So I have KL here, but I've got LK here, and DXL, tensor DXK. But, man, I got a lot of dust on this table. Anyway, so the antisymmetry of the components allows me to pull this bring this minus into play, and then you've got this antisymmetrized difference, tensor product difference of the differentials, which we defined in Lie to be the wedge product of DXK with DXL, and hence there's your formula, and there's proof, in fact, that gamma A, which is of course this subset, this set of the wedge product of increasing index differentials, is in fact giving us a basis, a pointwise basis for the set of smooth antisymmetric tensor fields of rank 2 on an N manifold. Now, so that directly proves span, and in fact, whenever you get an equation like this, if you think about it, you can just basically let this act. If you let this act on pairs of partial derivatives, you can easily say that this equal to 0 implies the coefficients are equal to 0, which then gives you the desired linear independence as well. So I would say linear independence pretty much follows from that equation if you just think about it for a second, or 3, or an hour or 2 if you were me as an undergraduate. Let's see here. So part C, I was supposed to, what was I supposed to do? Oh, take a symmetric tensor and show that it can be written as a sum of the symmetric tensor products. And so what I did, basically, was use the asymmetry of the components, Tij is equal to Tji, and I went through the same calculation I just went through, except the difference being that now I've got k less than L, k greater than L, and k equals to L, which I just did k, kk, dxk, dxk. Okay? I'm sorry, that's horrible. I regret nothing. And then I relabeled it to I and j like I did last time, and I left that one alone. And then I put them together using that Tij is equal to Tji. I factor that out. Now that is the symmetric tensor product of dxi and dxj, which Lie simply denotes as dxi dxj. And over here, actually, if you tilt your head and squint, you can see that's also the symmetric tensor product of dxi and dxi. Or you could write it I equals to j of Tij. I'm just forecasting the next move there, which is to say, oh, it's I less than or equal to j. Yay, we're done. And again, by similar logic, this shows spanning and linear independence. If you sort through it, you could write another couple of sentences here to convince yourself of linear independence. I'm just in a hurry, admittedly. Okay, guys. Now, here's some notations that I think are relevant. The covariant rank 2 tensors over M, which I've called B. Lie also has the notation sections of the second tensor. 2 covariant, I don't know the words, so I'm sorry guys. This is the covariant, not covariant, listen to me, the cotangent bundle, and 2 tensors over the cotangent bundle, and antisymmetric 2 tensors over the cotangent bundle. And so he uses omega 2 for that as well, which I've used BA for here. And as far as I can cipher, Lie doesn't seem to have a reserved notation for the symmetric tensors over the space. So, yeah, well, you know. Next up, problem 60. You're given that T is equal to that, and it's an antisymmetric tensor. I beg the questions, what if you write it this way instead? So that versus that. And actually, so that's kind of a dumb question given the one we just worked out, because that's already been answered. Like, the first question is, yeah, we just showed Tij is equal to Cij, so you're dumb. And then how did Bij, now this is a little bit more interesting. Notice here that the sum over I and j is it's not I less than j, it's I whatever, I and j over all values. So that's a little bit more interesting, and I kind of worked through that here. So basically, I rewrite t. First of all, I suppose it's equal to Bij dxi wedge dxj up there, and then I just sort through what that means. Well, actually, no, I didn't do that. I gave up on that, and I decided to do this instead. So I did I less than j, I greater than j, I equal to j. Of course, this is 0, so technically speaking, you can make BII whatever you want it to, but typically people make BII equal to 0, and typically people make Bij equal to minus Bji. And if you do that, and follow these calculations down here, eventually you'll get, well, actually, I didn't do that just yet. All I did was properties of the wedge product, and it eventually gets you to this, which then means, since dxk wedge dxl is a basis, I can equate coefficients here, and because of, so that's like that's the main issue with not doing I less than j, is like you're no longer working with a basis. So unless you're imposing some kind of conditions that link the related basis elements, you can get yourself into trouble. So like an example of this in linear algebra would be when we find the matrix of a quadratic form. If you don't make the quadratic form symmetric, you could still find a formula which would like work, but then you lose all like the cool bells and whistles from having a symmetric matrix. Similarly here, if you were to, for whatever oddball reason, choose to not impose that your b coefficients are anti-symmetric, you could still find an equality here, but then it would be a perilous business to like figure out components to tensors subject to such a condition. So I don't know. Anyway, so if we choose the anti-symmetric condition, we end up finding that Bij is 1/2 Tij, like that. And this answer is not unique, but it's usually what's done. All right, and if you have a rank, if you have like a p form instead of just a 2 form, you end up with a p factorial there because of the combinatorics. It just happens to be 2 because there are just 2 terms in the anti-symmetrization of 2 differentials. If you're doing the anti-symmetrization of p differentials, you get p factorial different terms as you sort through the different permutations. Now, 61 here. Oh yeah, we're just supposed to show that the tensor product here, and I decided I was just going to show associativity. I think I eventually guilted myself into showing more, but let's start with the associativity. I found this snazzy notation. Rather than writing a tuple of vector fields, I wrote a vector of vectors. So vector vector of vectors, vector vectors, 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 vector vectors, vector vector. These are the vector of vectors. Yeah. So great. So first of all, by definition of the tensor product, it's F tensor G acting on that and H acting on that. We are making use of identifications of like Cartesian products with Cartesian products. In other words, we're not distinguishing between like x, comma, oh goodness gracious, I don't even want to write down, but like, suppose you had x comma y with parentheses, comma z, versus parentheses x comma y comma z. Just one set of parentheses on the one and 2 set of parentheses on the other, but you're just grouping 2 inside of 3. Like, we're ignoring those kinds of distinctions when we write these things. All right, that's at play here. Anyway, it's either at play or I'm not reading his definitions carefully enough, but it could be both. All right. Anyway, so let me stop saying uninteresting things. So here we go. This is equal to that, and then we apply the definition of tensor product once more, which gives us this. But at that point, we can use the associativity of real multiplication to regroup things, and then regroup things back the other way, and then finally back the other way. But this holds for all inputs, x, y, z, tuples of vectors. Hence, the tensor product is associative when viewed as a here we're viewing the tensor product as something that you can do to multilinear maps. It should be mentioned that in the bigger course of abstract algebra, you essentially build the tensor product to be associative, through abstract algebraic chicanery. But there is a, a natural isomorphism between these different viewpoints, which you can learn about in an algebra class. Anyway, so the bilinearity, basically f1 plus f2, again, is this, and then by definition of addition of maps, you got that, which then distributes to like this because we have distributed property for real numbers, and then working the tensor product definition backwards, and then finally saying, oh, well, this equals to that for all x and y. Consequently, we have additivity in the first component of yield tensor product. And then I would say proofs of the additivity in the other component and the fact that you can pull constants out is very similar. Alright, moving on here. I got a lot to go through, and I'm going to run out of time if I'm not careful. So this one here... Oh, man? Really? Seriously? Oh, they decided to trim them. Wonderful. Wonderful. Alright, that's great. That's wonderful. Let's see here. Let's shake the mic. Let's put the mic level down a bit. Go back to about 35 here. So you hopefully hear me more than the trimmer. Children. I guess I'm happy they're trimming the yard, but, you know, the timing could be better. So here we were supposed to prove some properties of the symmetric product, and I think the most complicated one, of course, is the commutivity of the product is probably the most subtle part here, and it really just boils down to, when you look at the sum over all permutations, if you think about it, this ranges over all permutations, which means it ranges over all permutations of k vectors taken from the tuple of vectors v, and this ranges over all, you know, L vectors taken from v, and so that would be the same as if you just, of course you can commute these, you know, and then I have, you know, k vectors. Basically the point is that this sum and that sum are equal because of the fact that they're ranging over all permutations. So once we understand that, then the fact that alpha beta is equal to beta alpha becomes somewhat apparent. And the proofs of the other things really just really basically boil down to noticing that, you know, if we put this into here, then we can use the proper, like the definition of addition here to do, like, you know, let's see, my x, oh, I've called this x and I called that y to save some writing. So it's really alpha of x, gamma of y, and then beta of x, gamma of y, and I pulled out the constants a and b here, and then I used the definition of symmetrization again to get back to here, but then it holds for all v, therefore you got this alpha, a alpha plus b beta gamma equal to a alpha gamma plus b beta gamma, and the proof I think of the other part there is quite similar, which I'm sure you guys may have done because you know, once you figure out something, it's really hard not to write down the other thing because it's like, you know, I finally figured it out. I must write down the other one because the writing of the second one requires infinitely less time, right? Now this one here, oh, this is just the add-on for the symmetric tensor product of two covectors. So this one's kind of cute because if you just sort through what this means, there's only two permutations for two things. Either you go 1 goes to 1 and 2 goes to 2, or you go 1 goes to 2 and 2 goes to 1, which just leaves you with this. But these commute, so of course you can read this as alpha tensor beta acting on that tuple, and beta tensor alpha acting on the same tuple, which then, if you you know, use the definition of addition of tensors, basically it's always the pointwise addition of functions, guys. Like, it's just that. And so this holds for all v1 and all v1, v2, and therefore we have the desired formula for the symmetric product of two covectors. Problem 63 wasn't too bad. We're supposed to, you know, we have a rank k and a rank L covariant tensor field, and we're supposed to pull back that from over a smooth map. So the definition of the pullback is that I take a tensor b at f of p and I feed it the push forwards of the vectors inputted, But when I do that, by definition of the tensor product, it gives me A of all that stuff and B of all that stuff. But that's nothing more than the pullback of A and the pullback of B acting on the tuples of vectors, which then, by the definition of the tensor product of these guys, I pull the V out like so. And lo and behold, approved. All right, so anyway, yeah. This one, oh my goodness. This one, dang it. Man, this problem. Oof, I tell you. There may be a simple way to do this problem, but I have not found it. So what I did was I just came to the conclusion, I came to the terms that I need to do a proof by contradiction. And as such, I assumed that T is equal to, E1 tensor, E2 tensor, E3 is the sum of a symmetric and antisymmetric tensor. And then I sought a contradiction. And I sought, and I sought. And I came to some conclusions fairly early on, namely that if we look at T in terms of its tensor components, of which there are 27 in principle because we're working over 3 dimensions. So ijk, ij, and k, each taking 3 values, ranges over 27 possible values. Now, great. Now, and you can easily see that only T 1, 2, 3 is non-zero. And as such, we very quickly can get to the fact that 1 is equal to the 1, 2, 3 component of S plus the 1, 2, 3 component of A. And because A is antisymmetric, that is equal to S1, 2, 2, 1, 3, and S is symmetric, so S1, 2, 3 is equal to S2, 1, 3, and A1, 2, 3 is equal to minus A2, 1, 3. On the other hand, 0, when I feed E2, E1, E3 into the tensor, I get 0. But I also get, it's the sum of these two things. And so when you add these two equations, lo and behold, you get 1 is equal to 2 times S2, 1, 3, which gives us that the symmetric tensor 1, 2, 3 component is 1/2. And on the other hand, the antisymmetric 2, 1, 3, 1, 2, 3 component is equal to 1/2. And yeah, so in fact, any other component to the symmetric tensor has to be 0 because the antisymmetric one is automatically 0 whenever there's repeated index. So, goodness gracious. That brings us to the following assertions, namely, all of these guys are equal to 1/2. All of these ones are equal to either 1/2 or minus 1/2. And as such, I can build, and everything else is 0. As such, I can build E tensor 1, tensor 2, tensor 3, using this handy-dandy EIJK notation like such, as follows: blah 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 blah, blah 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 blah. Notice notice the juxtaposition of pluses for the symmetric piece and minuses for the antisymmetric piece, but only halvesies. And it's the halvesies and canceling out C's which gives us the troubles, because then we end up with 1/2 plus 1/2 is 1, so you get E1, 2, 3 is equal to E1, 2, 3 plus E2, 3, 1 plus E3, 1, 2, which then, lo and behold, gives us that the sum of these 3 tensors is equal to 0, but if you evaluate this on E2, E3, E1, this immediately gives you the equation 1 equals to 0, which is somewhat problematic. Therefore, there does not exist a symmetric and antisymmetric tensor, such that it's the sum of sum of that symmetric and antisymmetric tensor gives you E1 tensor E2 tensor E3. As I said, there's probably a shorter argument, but this is the one I found today. That's actually not true. I found it yesterday. But anyway, yeah. All right, like I said, I'm not letting perfect be the enemy of good. So here we go. Next up, you got problem 65. You got 2 isometric Riemannian manifolds. Show G is flat if and only if G tilde is flat. And basically what I've done here is just use properties of the pullback, because to say it's isometric means that there's the pullback of the tensor is equal to the Euclidean tensor, or vice versa, the pullback of the Euclidean tensor is equal to the metric tensor on your space. And as such, these things are done locally. Well, unless it's isometric Riemannian manifolds, in which case it's done globally. Anyway, here it is. So I have my isometry from M to M tilde. I've got the pullback of G tilde is G. Oh, that's part of that. And the pullback of G under big G is G bar. That's the Euclidean metric. So we've shown that the pullback of G tilde is also G bar, which shows us that M tilde is in fact flat, since it is locally isometric to Euclidean space. And a very similar argument works for the other direction, but I had to reverse some of the maps. And so here I kept F the same, but F's, the pullback of G tilde is fine, that's the same. But H I made different than the big G. H I went from M tilde Rn, the pullback of the Euclidean metric being the G tilde metric. and then when I compose H with F, that gets me from M to Rn, which then I'm able to pull back the G bar on Rn back to the G on M, and that shows that M is flat, which we say G is flat. Technically, it's always the pair, the space, and the metric, but in a pinch, we'll just say that the metric is flat. So, forgive me, it is a common language. This problem, way easier. So, you're supposed to show that the length of curves is an isometric invariant, and basically that just amounts to sorting through the definition. So we calculate the length of the curve is g tilde of the velocity vector of the composed curve, but because g tilde is isometric, because the manifolds are isometric, first of all, that's the pullback of g tilde under f of that, which then, because the manifolds are isometric, we have that this is the f pullback g tilde is g, which gives us this, which then by definition is the length of the vector. So that one I don't mind that one. If I was to give an in-class final, that would be my pick right there. That one everybody should be able to get. This one here, I chose to fall back on my physics roots for this. Again, my apology for the trimming. Yay, it broke. Ha ha ha. Alright, so we have Riemannian manifolds M and M tilde with the respective metrics G and G tilde. We can define the product metric G hat to be the direct sum of these metrics on the products M and M tilde. It's called the product metric. It's from page 329 in Lee. And alright, so basically what I did was say, okay, so if they're both flat, that means that you can, if G and G bar are both flat, that means with respect to the coordinates on X and M and M tilde, you can write it as just the sum of the squares of the coordinates differentials. That is one characterization of flatness. And as such, when you sort through what the formula looks like for G hat, it ends up just being the sums of the squares of the differentials in the product manifold, basically. And as such, it is flat. Now, I'm sure you could also prove that using the pullback criteria, but this is just the way that popped out to me. So if you don't like it, well, you can prove it a different way. It is a free country, at least in that regard. Let's see here. Just, don't say obvious things from the Bible too loudly. Okay, so here we have the N torus, and I thought this was just a twist on the previous problem, but actually upon further looking at it, I don't see as I can just use that the product of flat metrics is flat, because it doesn't say to construct the N torus as the product of the circles. It says to give it a metric which is induced from the Euclidean metric on Cn, which means I feel like a different argument is in play here. Like, I have to calculate the pullback metric for this problem. And so I did that. So here's the Euclidean metric on Cn, and Cn. Sorry. So here is a mapping from the angle coordinates on the torus to Cn, of course, just imaginary exponentials, which breaks down into the sine-cosine pairs in the real imaginary, decomposition of the complex coordinates, the usual thing, the standard isomorphism of Cn to Rn, R2n rather. And if you calculate the differential of cosine and the differential of sine, you get these things and those things respectively. When you take the sum of the squares, you get the sum of sine squared and cosine squared, which just gives you the differential of the angle squared, and that happens for each one of the coordinates from 1 to n. And as such, the pullback metric of the Euclidean metric onto the N torus is nothing more than the sum of the angles squared. But that's a manifestly flat metric on Tn, because the components of the metric are exactly the identity matrix with respect to the angle chart in Tn. So there you go. Let's see here. Where are we? Oh, problem 60. So you guys warned me that I doubled up. Oh man, look at that. Alright, so I guess that is the end for mission 6. Coming in at 30 minutes. That's not good. Alright. Mission 7. Try to pick up the pace here. Submission 7. Somehow we have regressed to problem 67. Oopsies. Uh, that's interesting. Sorry about that. Okay, so I know it's kind of depressing. You feel like I already finished 67 and 68, but then you're back doing them again. But here they are. So these ones might be more interesting. The problem previously known as 67. So here, here I've used some rather sneaky notations, perhaps. Maybe not this one. So I have pullback. I'm supposed to prove properties of the pullback, and so I just chose to use the definition, the alternate, this alternation thing he did, as like a shorthand for the sum over all permutations as such, because that kind of summarizes the point nicely. When we take the pullback of omega wedge eta, it's the pullback of this, which is really just a fancy notation for a sum of a whole colossal stupid number of tensors of omega and eta. But as such, this alt property is well, first of all, the pullback is linear, so I can pull the constant out. But the alternation thing is also essentially a linear, so I can pull it out because it's just a plus minus sum of things, So I can pull that outside of the pullback by the linearity of f star as well. And as such, and then I use the property of the pullback from before, back in the earlier chapter, to get me the tensor product of the pullback of the tensor is tensor. I think we did this in the last homework, and then of course I've got exactly this anti-symmetrized sum of these tensor products, and as such that's the wedge product. So yeah, there. Now I'm sure in a different notation that could have been much worse, but yeah. So, and I think I did a similar kind of sneaky business over here. Let's see here. So here I'm proving, what am I doing? Well, I've proved the linearity of the pullback here. Here I just chose to look at it in terms of the definition as it relates to, like, push forwards, and so there it is. I don't really have anything to say about that. And this down here, the formula for the composition, basically the substitution formula derivation, what it boils down to is, if you're calculating the pullback, all this, what you're doing is you're evaluating this thing at f of p, and you're feeding it the push forward of the vectors under the f map, right? But what that really means is this sort of gory anti-symmetrized product of all these things, according to the wedge product. And when you look at that by the chain rule, that's each chain rule each time, differential of y composed with f, and on down the line, and it's the same anti-symmetrization happening. And then what does that mean? Well, that just means take the wedge product of all those things by the same anti-symmetrization product. So like I said here, I've used this wedge, quote-unquote, to denote the complete anti-symmetrization of the product in question, which amounts to the details of the wedge product. Sorry. Yeah, me lazy. Mucho sorry. So here, this problem was easy. Let's see here. So you got the formula relating the exterior derivative to the Lie algebra, the Lie bracket of vector fields, and enter the so-called structure constants of the Lie algebra. He doesn't call them that, but that's what they are. These are the structure constants. And he shows that the coefficients of the differential of the coframe are, in fact, minus the structure constants in this sense. It's pretty nice calculation. When you hit this on that, and you think about what this means and how that works, it just picks out Kronecker delta JL, Kronecker delta KM. As such, this picks off BILM, BLM, and sorry, none of that in here. And then likewise, if I calculate this with the formula, this is a vector field acting on 1 or 0. 1 or 0, those differentiate to 0, because remember, EL and EM are derivations. and this survives, but this is the structure constants. Pull them out, Kronecker delta, bam. Yep, that one wasn't bad. Again, if I was to give an in-class final, that would definitely be on my list. Now, so show covectors omega 1 through omega k on a finite dimension of linearly dependent, if and only if this. Alright, yeah, so the forward implication is pretty simple, because basically all you got to do is notice that if you write one as the sum of the others, when you take the wedge of all of them, you got to repeat in every term in the sum. And anytime you got to repeat of the wedge product of two one forms, you get 0, and as such it's 0. Now the other direction, I found ways to make it complicated. I think this argument down here, it's legit. If the, suppose the wedge product is equal to 0, all right? And suppose that the omega 1 through omega k are linearly independent, then let's say W star, the span of the W1s through WKs has a basis, W1 through WK, dual to E1 through EK, and as such, when we take omega 1 wedge omega k and act on the basis to which it's dual, we get 1. Which then means that the wedge product of omega 1 through omega k is not equal to 0, which is a clear contradiction to the fact that it's equal to 0. I think that's a legitimate argument. But let me show you what I did past that. So before I found that argument, I made all these arguments. Well, actually, you know what? Let me not talk to you about all of what I did here. But basically what I did was I found coordinates so I extended to a basis or something like that, I think, and then I found like components, and I eventually boiled it down to this lemma that if you have covectors which with coordinate vectors, in the sense that you can build your covectors from a sum over a basis like such, and you have the wedge product of the alphas being 0, then the wedge product of their coordinate vectors is also 0. And yeah, so I will post these things. I do think there's actually some decent calculations in here, but the proof I gave you like 2 pages ago I think is like a legit proof by contradiction anyway, so yeah. But here's the proof of the lemma. It involves some of my favorite calculations, namely that if you have this like sum over coordinates, you can wedge product of those things, you can pull out the sum over all these, and then what's done is when you've got the wedge product of all these guys, you can replace it with the Levi-Civita symbol with the anti-symmetrized indices here, and then just theta 1 wedge through theta k. But then you look at this is by definition, well, my definition, in my linear algebra class at least, maybe not in lay, but this is in fact the real honest-to-goodness definition of the determinant of the matrix formed by the concatenation of the coordinate vectors of the theta 1 through theta k, and there you go. And then, of course, the rest of it falls out from there, but I don't know. Like, these calculations are interesting, but I should have written the problem in a different way if I wanted to lead you to those calculations, so my apologies. Cartan's lemma is a standard result. You guys probably have found a good solution to that somewhere else. I had a good solution of it written in my solution to Mission 5 of Advanced Calculus 2015. It's actually like very close to the end of my homework set from Advanced Calculus 2013. It's there too. Oh goodness gracious. Problem 71. You're supposed to calculate the this differential, this two form actually in spherical coordinates, and so I did it. And yeah, I did it. And some stuff cancels, and some more stuff cancels, and some more stuff cancels, and then bam. That's what you get. Omega rho squared sine phi d phi wedge d theta. That's what I got anyway. Or rho cubed sine phi d phi wedge d theta. That makes sense to me for reasons that will become clear as we go on. So, and we're supposed to then calculate d omega both in Cartesians and sphericals. Now in Cartesians, it's pretty obvious. It's just 3 dx wedge dy wedge dz. And in the sphericals, if you just differentiate the formula we found before in sphericals, that just gives you 3 rho squared sine phi d rho wedge d phi wedge d theta. But, by the way, fun fact, the Jacobian determinant that you learned in Calculus 3 is how the differentials of the Cartesian relate to the differentials of the spherical, and as such, dx wedge y wedge dz is also equal to rho squared sine phi d rho d phi wedge d theta, which gives us, of course, also that d omega is 3 rho squared sine phi. So anyway, it all works together. Now, the pullback of this omega to the one sphere is just given by this, because we just set rho equals to 1, so that's the pullback. And to see that that's non-vanishing on the sphere, well, this is just giving us the pullback where the angle functions are defined. But if you think about it, the way that omega is defined, it's completely symmetric. If you look at the formula, with respect to x, y, and z, there's a complete symmetry between x, y, and z. So if you can set up the spherical coordinates such that the z-axis has its particular role and the xy plane has its particular role, then you can just as well set up spherical coordinates with respect to the x playing the role of the z or the y playing the role of the z. And as such, each one of these choices of modified spherical coordinates gives you that the pullback of omega on that respective portion of the sphere on which those modified spherical coordinates are defined is non-zero, and when you take the totality of the union of these cases, you get the whole sphere. As such, the pullback of omega is non-vanishing 2 form on the sphere, which means, in fact, it's an orientation form. Now, fun fact, you could also look at this calculation like a different way. I didn't talk much about this semester, but S2 is the inverse image of 1 for this map. The differential is 2x dx plus this. The Hodge dual of the differential is that. That's exactly omega, well, divided by 2. So omega is actually 1/2 the Hodge dual of df as such. And so for what it's worth, d omega is the differential of the flux form of the gradient, which is the divergence of the gradient, which works out to 3 dx wedge dy wedge dz. So there you go. Another way to look at this. You may remember the three-dimensional calculus differential form stuff I talked about one day. I guess I talked about a lot of things. I don't think you guys will have much trouble with this one. It's pretty straightforward. I'll just kind of scroll through these results. I won't say anything. You can check your work, I guess. Once I get to school, I'll scan them. I just don't feel like scanning it with my phone at the moment, so I'm making you this annoying video instead. Hehehe. Yeah. That's actually the Coulomb field, that last one. And so, it concludes my 12-minute run through Mission 7. Let's see if I can get it down to 5 minutes for Mission 8. Alright. Mission 8. Yeah, I'm not sure if I have much to really offer you here. Let's see here. So, this was problem 73. We're supposed to prove the following are equivalent. Now, I feel like I've got a decent proof of A implies B, so like if I assume A, D is involutive, then I got these smooth defining one forms. And then theorem 19.7 tells me that d omega 1 through d omega n minus k also annihilate d on U. So like theorem 19.7 gives me that implication. If I suppose B is true, then I've got the d omega 1 through d omega n minus k annihilate d. But then lemma 19.6 tells me that if I take eta equal to d omega I, then I find smooth one forms, because p equals 2 gives me p minus 1 equals to 1, so I can set my quote-unquote beta ij from the theorem equal to alpha ij for the sake of this particular claim. And that gives me that d omega I is equal to that. So B implies C. And then assuming C holds true, that I haven't done. I need to show C implies A. I'm hoping you guys can tell me how to do that when we meet tomorrow. All right? So there's that one. Yep. And then, so there's going to be a few gaps in this problem, these solutions. We're supposed to show it's an ideal. This one I think is pretty simple as it goes. So suppose you got D is annihilating one forms. Suppose you gamma is in the ideal. What is that noise? Okay, it's outside. Fine. Then gamma annihilates D. Thus, by lemma 19.6, there exists smooth forms beta I such that gamma is the sum over the defining one forms omega I, right? But then if we take any other differential form over the manifold and we wedge it with gamma, we can rewrite the wedge as a wedge product of omega I with this thing, but that's a smooth form, and then again by lemma 19.6 that implies that eta wedge gamma annihilates D, which is to say that omega wedge eta wedge gamma is an element of D, which proves that J of D is in fact an ideal. That's pretty cool. Problem 75. Wasn't too bad, I guess. We got this vector field, that vector field, and so calculate the flow. Yeah. So here's my defining conditions for the integral curves. Integrate those things. Change my x naughts to x, my y naughts to y, my z naughts to z as such down here. That usual thing I did. That gives me the flow. Likewise, integrate these. And that, so I got the flows from integrating. I bet you guys get that fine. Now I did it a different way when I was talking to you guys, but here's the way it occurred to me today. So basically, to show that this is an integral curve, integral surface manifold to the distribution, one way I could look at it is this is a level surface of z minus xy equal to c. So the gradient of the level surface is minus y minus x1. And I just want to show that v and w are tangent. So if I take the dot product, the inner product, if you like, of the vector fields with the normal vector field to the surface, if I get 0, that means they're tangent. Indeed, the dot product does, in fact, give me y minus y and x minus x, which is 0. As such, v and w are perpendicular to the normal, to the gradient of f, which means that v and w are tangent to the surface defined by z minus xy equals to c. And yeah, so that means that z minus xy equals to c are integral manifolds of D. So the way I did it with one of you was more in terms of differential forms. That might have been a better way. It just didn't occur to me today. Now this one here, I've got half of problem 76. And I'm not sure what to do with the other. I'm not saying it's hard, I'm stuck on it at the moment. Maybe you guys can explain it to me. So if D is involutive, that means we got these annihilate D on U. But we also have that d omega I annihilate d on u by proposition 19.8b, but then that means that we can write d omega as the wedge product of omega with some other forms. And if I plug that into this grand glorious wedge product, then I definitely have a repeat of omega j somewhere in here for each j equals 1 to n minus k, and as such, this is the sum of 0 plus 0 plus 0 plus 0 plus 0, otherwise known as 0. Great. The other direction, I'm stuck on at the moment, so maybe you guys will explain to me how to do it tomorrow. Now, let's see here. Oh, this one's fun. So here, this is, I call this Pfaff's theorem, basically. The forward implication, if we have that there exists an integrating factor, so a positive function mu, such that mu times omega is exact, which means that it's the differential of another form alpha on u, then if we take the wedge product, if we take the differential of this, we get d mu wedge omega plus mu d omega equal to d alpha, which is also known as 0. And as such, I can solve for d omega minus 1 over mu, d mu, wedge omega, which tells us that omega wedge d omega is equal to 0 on u. There we go. But u is arbitrary, so we've got that d omega wedge omega is identically vanishing on such a manifold. Now the other direction is a little bit trickier. I sent you guys an announcement about it earlier today, but here's a sketch, I think. If this is identically equal to 0, it follows that the distribution with the annihilating form omega is involutive on M. Hence, by the Frobenius theorem, this is an n-1 dimensional distribution, which means it's completely integrable. Thus, there's an n-1 integrable manifold aligned with D. As given local, we can write the integral manifold U as a level surface, something like f of x equal to 0, with df equal to 0 on U. Then df is equal to minus omega wedge mu. By lemma 19.6, the mu has to be a 0 form, because df is a 1 form, omega is a 1 form. It forces mu to be a function. And then we can either we can change f to minus f if mu is positive already. Mu can't be 0, because if it was, it would make df equal to 0. And if df is equal to 0, it's no longer the case that you're looking at a n-1 dimensional function. So that's how that goes. B is just fun. If you've got d omega wedge omega, well, that's equal to 0, because that's a 3 form, and in 2 dimensions it has to be 3. Therefore, there has to exist an integrating factor in some neighborhood at each point in M. And I think that probably is what I should call Pfaff's theorem from differential equation. At least that's what my brother called it. This one here, I made this much harder to start with talking to one of you. You know who you are, Preston. And, or was it Ernesto? I can't remember. I think it was Preston. But anyway, after about an hour or so, or a half hour, I forget exactly how long, it hit me. Duh, the xy plane is the integral manifold. So yeah, like xy plane, if you look at it, restrict x and y, you get partial x, partial y. That of course, those are tangent to the xy plane, and so that makes the xy plane an integral submanifold passing through 0, 0. The point of this, though, is that if you calculate the Lie bracket, you get minus z partial z, which is not in the distribution. Therefore, D is not involutive. It fails the Lie bracket closure condition. But so how does this work then? How have I found an integral submanifold if it's not involutive? Well, the theorem is that I can't find integral submanifolds that fill out the whole space, right? I can't find integral submanifolds of D which foliate the space. That doesn't mean I can't find one somewhere. I did find one somewhere, the xy plane. And that's okay. And moreover, if you look at it, if you think about restricting the distribution to the xy plane, it's involutive there, and in this rather silly case, S itself is the integral submanifold. So anyway, I think that's kind of the point of the problem. And it's also why, when we looked for solutions to the problem, we kind of found answers, but we never really found very much follow-up, because I think kind of the end of the answer is like, oh, that's not that interesting. Problem 80. Oh, I guess there's a problem 79. I skipped that one for some reason. Anyway, I will try to go back to it. Maybe we can crack it. I've spent like 2 hours on that problem already. So anyway, sorry, that one's hard. My comment notwithstanding. Anyway, so here we go. Lie group, suppose that H is a Lie subalgebra of G. Explain how the Lie subalgebra of frac H can be used to define an involutive distribution on G. So here's a sketch of the proof. So basically, oh, oopsie. I knew I'd need this somewhere. I have mislabeled my Eins element. There we go. So, we don't discuss our identity around here. We have the Eins element. So the tangent space at the identity of G is isomorphic, of course, to the Lie algebra of G, which is also isomorphic to the left invariant vector fields on G, as we kind of discussed. And basically, the idea is I can construct a subalgebra of the left invariant vector fields on G, and as such, that will actually serve as the desired involutive distribution. And so basically, here's how you do it. You just define the left, like the vector. This is notation I use just for this problem. If I have V naught in the subalgebra, I can move that thing around by pushing it forward under the left multiplication, the differential of the left multiplication by G map, based at the identity. So that takes me from a vector at V to a vector at G, like so. And when you sort through these things, as maybe we did, I don't remember. If I didn't, I'm sorry. I've tried, but yeah. Anyway, at some point, if you're interested in these things, you should take a whole course on Lie groups. Like a whole course. And anyway, so long story short of it, this is the identity which is satisfied for that the Lie bracket of the vector fields defined in this way is actually the same as the push forward of the defining vectors. And what that means is that if you have two vector fields in this subalgebra of the left invariant vector fields, then the bracket of said vector fields is again such a vector field, which shows you that this curly H thing is in fact involutive. And there you go. That's basically it. Here's your homogeneous spaces from chapter 21 in Lie. So for your collecting purposes, there you got your collection of 5 homogeneous spaces. Hooray! I think that's the upper half plane. But anyway, again, you could take a whole course on homogeneous spaces, yeah? Depending on which school you go to, I suppose. Not everybody cares that much, but there was an expert at NC State in my time, although I imagine he's retired. All right, so what remains are missions 9 and 10, and these, I already have much more help for you. Don't really have to say, I think I pretty much worked this out in class. This you'll figure out. This is solved in the notes that are linked to the course planner. I think if you think about what we did in class, you can answer this. This is a straight calculation based on the definition. You can do this. Yeah. These are pretty straightforward calculations. you know, make sure you, I want to say you use the formula we derived. Like, I don't think I did these on the basis. Yeah. Oh, but again, these are, I think, all proved in my course notes that I have linked for you guys. Not the course notes, but like the handwritten PDFs I'm talking about, you know. This, I think I did this calculation pretty much in class for problem 88. You really should find these last homeworks a kind of a welcome relief from the uncertainty and the sometimes deep water in the Lee problems. These are all close to shore, and the life preservers are posted on my website. You know, yeah, I don't think I have anything particular to say about all these. They like, some of these are just straight calculations, and I think the answers, if they're not in my notes, they could be easily found online, just to check yourself. Mission 10, again, I think I've done a great number of these calculations in class, actually. Goodness. I'm looking forward to writing the solutions out for these two. I really hope I get to it today. There might be something in here interesting. I don't know. So hopefully I'll get to those, but I haven't got to them yet. So hopefully I'll get to them before tomorrow. Anyway, I'm hoping maybe, I don't know, like, I have two ideas. My one idea is just to go La Coretta. My other idea, which I think might be better for us, is if I could get some food and then we could just kind of hang out and have supper and look at the PDFs of things together, just to wrap things up in the evening. But if we wrap things up before the evening, maybe we can just go to La Coretta. I don't know. Something like that's we're gonna do one or the other at 6. I'm not sure what yet. So anyway, thanks guys.